Hello and welcome to this webinar. I'm Gabriel Rojas, Application Engineer at Rohde & Schwarz, and today I'm going to talk to you about parasitic components in power converters, fundamentals and measurements. Let's start with the agenda. First, we will see the motivation to this webinar, following by the introduction to parasitic components. Then I will explain how to measure these parasitics, followed by a brief explanation of the LCR meters as a solution, and finally a demo. So let's begin with the motivation. Among the greatest challenges in modern power electronics is testing systems with wide bandgap materials, such as silicon carbide, gallium nitride, and so on. These materials have many advantages as well as many challenges, especially in testing them. These technologies provide higher power density, which lead to faster commutation of transistors. Here in the chart, we can clearly see that GaN technologies are reaching 1 MHz and is expected to grow this frequency in the following years. This is a problem and a challenge for nowadays power electronics because parasitics will appear in our converters and we have to consider them when we are doing our design. Also, this will have an influence in conductor emissions, and then it's important to quantify these stray components at the early stages of the design. Here we have a basic design methodology for power converters. In this design flow, we start with a pre-design. In this case, it uses the main specifications of a DUT, for example, the input voltage, the output voltage, the power that is needed, and the pre-design is done. After this, the design is validated in software. Then the components are selected based on the main requirements of the system. It's important to mention that in these early stages, the parasitic components are roughly estimated or not considered at all. This is due to the fact that there's not too much available information, there's lack of information in many datasheets, so that's why it's not considered in these stages. After the components are selected, there's another software simulation and correction. In this case, it is the converter is corrected and the design is improved based on the components that have been selected. After this is proven, then we follow into a new stage, which is the experimental validation. A prototype is manufactured and validated. In this case, if it is working as expected and the results match the simulations, the experimental results, well, then we can go to a EMI pre-compliance stage. If not, we'll have to do the redesign. This redesign might be necessary depending on the effect of parasitic components. If we don't consider them, we will have a significant impact on the behavior of our circuit, and the experimental validation will not resemble the actual simulation that we did. A way to tackle this problem is to characterize the passive components in the early stages of the design, if possible. This is done by measuring these components at the early stages, characterizing the parasitics that it has, and this will help to bring closer the simulation and experimental validation. Therefore, we will save time without having to do a redesign multiple times. Another important aspect that we are facing nowadays is the lack of information. Sometimes the information provided by the manufacturer is limited and we don't have that many information regarding the components that we are using in our converter. Or even if the information is given, there are major issues that we need to be aware of. First of all, the tolerances. In some converters, in some components, they go up to 25%. So for example, if we have a capacitor of 100 microfarads, it could easily be 125 or 75. So it's really important to consider this tolerance. Then we have the test conditions that will also influence the value that we get from the datasheet. In this case, it could be voltage, frequency, and these test conditions normally are different than the ones that we need because our application is unique, is different to the one that, for example, the capacitor manufacturer think of. So the test conditions are different, and this is really important to take into account. And finally, the temperature. This could be in the test conditions, but I put it separately because it's as equal as important, and it's important to consider both the operating and ambient temperature. Now, having explained the main motivation to consider the parasitics nowadays, I will go through them and I will explain what is meant by them, what is meant by parasitics. In electronics, parasitics refer to undesirable components or effects that accompany the intended electrical behavior of a circuit. These components can include capacitance, inductance, resistance, and impedance, and they can affect the performance of the circuit in unintended ways, such as reducing its efficiency, accuracy, or stability. For example, we have here a transistor, and we can see here that the model with its parasitics. We can see that the complexity increases, as well as with the capacitor and the inductor. So it's really important to consider both cases, the simple model and the model with parasitics, because it will increase the complexity in our circuit. And there is a question that always arises, and this question is it always at high frequencies? Well, the answer is yes and no, and it's no because the parasitic elements can exist also at low frequencies, because it's a characteristic inherent to the passive component, but on the other side, the impact is less noticeable at these lower frequencies. So that's why they are not considered, because they won't impact the performance of our converter if we are working at these frequencies. However, working at higher frequencies will have a higher impact, and the overall performance of our circuit will be affected. Where I can find those parasitics? Well, they can be found in various parts of a circuit, starting with the interconnections. The parasitic capacitance and inductance between two conductors in close proximity can affect the signal transmission in high-frequency circuit, for example. We can find them also in passive components. So these parasitic elements are inherent to these passive components, such as capacitors, inductors, resistors. Also, we found them in integrated circuits. These parasitics can exist in ICs due to the physical layout of the components and the interconnections of the chip. Then, in packages, so the package of an electronic component can also introduce parasitics, such as the capacitance between the leads of a packaged component. Then we have the printed circuit boards. The parasitics in a PCB can come from either the trace geometry or the spacing between conductors, and also the material properties of the PCB substrate itself. So in the end, we have different parts in our circuit that have parasitics that we have to consider, and as I already have explained, they are everywhere in the circuit, so it's really important to take them into account when we are doing our design. And how do they appear as these parasitics? Well, they can appear in three forms. First of all, as a parasitic inductance, which arises from the magnetic field created by the flow of current in a circuit, such as the loop created by a trace on a PCB. Then we have the parasitic capacitance, which arises from the close proximity of conductive elements in a circuit, such as the metal interconnections on an IC or the leads of a passive component. And finally, we have the parasitic resistance, which arises from the resistance of conductive elements in a circuit. To have a more in detail explanation, here we have a simple model of a MOSFET transistor, and then we have here the parasitic capacitances that it has. These capacitances arise between their terminals, and they are inherent to the silicon component, or if we are using another substrate. So these parasitics capacitance are formed during the manufacturing process, and we as design engineers, we cannot do nothing about it, we cannot minimize it, but we have to consider them in our design and, if possible, characterize them. On the other side, there are the external parasitics. In this case, they are normally inductors that are formed when the packaging occurs or due to the bonding interconnections. Also, they appear when we are probing the terminals. These parasitics can be minimized, and is a task of the design engineer to do a proper package, to do proper interconnections in order to minimize these parasitics, because these ones can be optimized. So in summary, in transistors we can find internal parasitics, which are silicon-based, normally capacitances of the substrate, and also external parasitics, which are formed due to the bonding interconnections and probing. Moving on to passive components, we will focus on the following components: inductors, capacitors, resistors, and transformers. They could be wired or SMD type as well. So let's begin with capacitors. The characteristics of a capacitor depend on the dielectric material, the capacitance value, the construction details such as contacts and packaging, and so on. Here in this graph we have 6 different capacitors which have the same capacitance value at a certain condition with 0 DC voltage bias, and then a DC bias is applied. We can see that for the multi-layer ceramic capacitors, there's a significant capacitance change rate, almost 80% in a case. So this is really important to consider and to take into account, because depending on the dielectric material, our capacitance value might change also with the operating condition. So it's really important to know this when we are measuring our capacitance. The test conditions that are normally used for these capacitors are frequency, amplitude, and bias voltage. We can see here in the graphs that the capacitance, this example, increases with the frequency, and for frequencies between 1 and 10 megahertz, it increases rapidly. The same happens with the amplitude level. We can see here that the capacitance increases with the AC voltage injected to the capacitor. And how do we model this capacitor? Well, here is, this graph explains how to model it. For example, for lower frequencies, it will have a high impedance, and the capacitor is modeled as in parallel with a resistance, as you can see here in the graph. Then there's a transition point at a certain frequency where the capacitor is modeled in series with the resistance. This is the model that we can see in datasheets. For example, the manufacturers provide us the capacitance value with the ESR, or equivalent series resistance. And after this point, the impedance keeps dropping until one breaking point where the capacitor will start to exhibit an inductive behavior due to the parasitic inductance that it has. And from this point, the impedance will start to increase, and the capacitor will behave as an inductor. Then let's move to inductors. So the observed characteristics of an inductor depend on the measurement settings as well as with the capacitors. But also there's some potential errors that we have to consider that depend on the construction of it. So if we have an air core of our inductor, it's not critical, the measurements won't be affected at all. However, if we have a magnetic core, this core can saturate depending on which frequency we are measuring or the DC current applied to it. So it's really important to consider this when we are doing our measurements. The core shows residual magnetism or hysteresis, and the AC current flow is no longer linear. So it's really important to consider this and to know these differences between the different type of inductors. Then it depends as well on frequency, on the DC current, and on the temperature. And here, for example, we have 2 series of inductors. The ones in the charts above, you can see clearly that the inductance value decreases with frequency and also decreases with DC current. For another series of inductor in the graphs below, we can see the same behavior, of course with different inductance values, but the behavior is overall the same. And also, depending on the temperature, it will change. Now, let's explain a little bit about its model. This model, it's the opposite to the one of the capacitor, and you can see here clearly in the graph. In this case, for lower frequencies, we will have a low impedance. The inductor is modeled as in series with a resistance, and after a transition point, it will be modeled in parallel. So we have here, for mid-frequencies, the inductor in parallel with a resistance. The impedance will keep growing until a breaking point, and after this breaking point, the inductor will start to behave as a capacitor. This is thanks to the parasitic capacitance of this inductor, and the impedance will start to decrease. So now let's move on to resistors. Resistors do not have a frequency dependency. We cannot find in data sheets that they depend on frequency or its value changing frequency. We can find these values in their datasheet, such as resistance tolerance, parasitic capacitance, temperature coefficient, and voltage coefficient. However, it is really important to consider that resistors do have a dependency on frequency. For a high value resistance, the stray capacitance will dominate, and the resistor will be modeled as in parallel with this capacitance. So for low and mid frequencies, the impedance will be constant with an angle of 0, but after a certain transition point, the impedance will start to drop, and the resistor will behave as a capacitor until it reaches the minus 90 degrees. The opposite happens for a low value resistance. The lead inductance dominates in this case. The resistor is modeled in series with this lead inductance, and here we have that for low and mid frequencies, the impedance will be constant with an angle of 0, and then after a certain point, this impedance will increase and the angle will increase as well until it reaches the 90 degrees. In this case, it will behave like an inductance. After explaining where to find the parasitics, in which components, how do I model these components, let's see how these parasitics affect my measurements. So first of all, there will be a distortion of voltage and current waveforms, which may lead to reduced efficiency and increased power loss. There will be unwanted resonances, which also leads to power loss, increased EMI problems, and reduced system stability. Then we will have mismatches between the passive component and the surrounding circuit, and this is mainly because the circuit is designed in one way and not considering the parasitics. But since these passive components has different parasitics at different frequencies, there will be a mismatch between the design circuit and the passive component itself. And this will lead to a reduced efficiency and an increased power loss. Then we will have stability issues, which also lead to power loss, increased EMI, and reduced system reliability. And finally, the switching losses will increase, which in the end leads to a reduced efficiency. You can see here that overall, the main problem of not considering parasitics and of having parasitics in our circuit is the reduction in the efficiency, and it will have an impact on the overall performance of it. So here I will show you an example of how the parasitics affect our simulations. So we have here a basic topology of a boost converter. To the left, it's a basic topology with no parasitics at all, nothing is considered, and this is the basic one. Then to the right, we have a simplified topology. The equivalent resistance of the capacitor and inductor was considered, and the values used in the simulations were the ones given by the manufacturer. And in the bottom part, we have the complex topology. Here, we consider parasitics, and the components have been characterized as well with their different parasitics value, and we are also considering the parasitics of the transistor. So let's check the simulations. So in green, we have the experimental data, the actual data of this boost converter, and we can clearly see that for the output voltage, the response is completely different for the first and second topology. Also, at the output current, we can see that the transient response is way different. It takes way more time to reach the stability point, and In the end, this is an inaccurate result. It does not resemble at all to our experimental data. However, the final topology, it actually resembles to the data and gives us a very good approximation on how the converter behaves and how it behaves when there's a load change, for example. Let's move on to another example. Here we have a buck converter, and here we have its schematic. It has 4 different capacitors at the output. 2 of them are ceramic and 2 of them are aluminum electrolytic. The ceramic ones are small capacitors which affect the output ripple, while the electrolytic ones are large capacitors that affect the transient response of the converter. So what we will do here is to change the values of the electrolytic capacitor to see how the response changes. So first of all, we change the ESR of this capacitor, maintaining the capacitance as constant for these 3 cases. We can clearly see here that the response is completely different. For the different equivalent series resistance, there's a different overshoot. The time to reach stability is different in the 3 cases. In this case, we can say that it's very sensitive to these changes, our converter. The same happens with the capacitance value. Now we leave the resistor as constant, and then we move the capacitance value, we change it. And we can see here that the transient response is completely different in the 3 cases. So it reaffirms that it's really important to characterize properly our different elements in our circuit, because this is for just one parameter. Imagine that, and it's the reality that we have multiple parameters in our circuit, multiple passive components. If we do not characterize them properly, we will have a problem, and we will have undoubtedly a mismatch between simulations and actual experimental results. And having explained this, let's see how to measure parasitics. Well, there's actually 2 ways. The first one of them is to perform online measurements. In some cases, the passive components of a converter can be characterized while the circuit is live or while it's on. To do so, we use the current and voltage signals and do mathematical operations to estimate the values of the passive components. An example of this is the in-circuit characterization of an electrolytic capacitor in a switch mode power supply. The current and the voltage drop across the capacitors are measured, and the capacitance and equivalent series resistance are estimated. There's an app note and a webinar on demand available in our webpage where you can find more detailed information about this application. In general, these online measurements are done using oscilloscopes and probes, and it has the advantage that we are working at the operating point of our converter, so we have a reliable measurement. However, it's not always easy to access to the different signals in our converter. The other way to characterize our components are the offline measurements. Here, the passive component is characterized when the circuit is off, and the test conditions must resemble to the actual operating point of the component. The ripple, the offset, the temperature, and the frequency must be the same, or at least similar to the ones that we are using in our converter. The LCR meter is the perfect tool to perform this characterization. The overall process for this offline measurement is the following. First of all, prepare the passive component. We remove the passive component from the circuit if necessary, and we place it near our LCR meter. Then we select the proper fixture. It could be a Kelvin clip, the fixture to measure SMD components. It will depend on our DUT. After this, we select the measurement type. Depending on the type of parasitic element being measured, we select the appropriate measurement mode on the LCR meter. So, for example, if we are measuring the parasitic inductance, we select the inductance measurement mode. Then we set the operating point. In this case, we set the frequency, the voltage or current level, and the voltage or current bias. This is in order to resemble to the actual application that we are using this DUT for. And then we perform the measurement. So once the measurement mode, frequency, fixtures have been set, the measurement is performed, and we follow the instructions of the LCR meter to obtain its result. Finally, we repeat this process for different measurement types if necessary. So for example, if I already measure the parasitic capacitance, I then change it for the parasitic inductance. This is an example. To understand better the LCR meters, I will briefly explain how they work. This LCR meter consists on an auto-balancing bridge. So basically what it does is to inject a signal into the DUT, that is our passive component under test, and it measures the AC voltage across it and also the AC current flowing through it. With these two quantities, the complex impedance of the DUT is calculated at a certain operational point. So in the end, the LCR meter measures the complex ratio between voltage and current. From this measurement, we can calculate every other parameter, such as inductance, capacitance, resistance, and so on. So here we have the different parameters that we can derive from this complex impedance. They are series resistance, series reactance, inductance, capacitance, dissipation, and quality factors. And here we have the graph. So in the end, we will obtain a result, as a result, the impedance with its angle. And depending on this angle, we will know if our DUT is behaving more in an inductive wave, such as angles higher than 0 degrees, or in a capacitive way for angles lower than 0 degrees or negative angles. For a resistive DUT, we will have angles close to 0. A very important aspect to consider when we are especially characterizing components for power electronics is the DC bias. Normally, our components are working at certain voltage levels, higher voltage levels, so we have to resemble this operating point, and to do so, we can inject a DC bias into our component in order to obtain the behavior at this point. For example, for ceramic capacitors, there's a change in the capacitance value depending on the bias voltage. The same happens in inductors, and this is mainly due to the core that exhibits a nonlinear behavior. So it's really important to consider this DC bias, especially when doing power electronics applications. Okay, now we have here the interface of our LCX200 LCR meter. Here we have the different parameters that we can measure. In this case, we are going to select the capacitance and series resistance, as well as the impedance and its angle. Here in the functions, we could select also inductance, resistance, or capacitance, but we are selecting capacitance. Then we set the different operating conditions. In this case, since it is a smoothing capacitor, we just set 50 Hz, a voltage level of 1 volt, 0.1 volt RMS, and 0 volts of voltage bias. Here we have our value, and we could easily go, for example, to 1 kilohertz. We can see here that now the angle has increased. Now it's exhibiting a more inductive behavior. And if we keep going up, for example, to 10 kilohertz, this angle keeps growing until eventually it will reach a point where it behaves completely inductive. So in this case, we are measuring the capacitance. However, it's not possible to measure it because this capacitor is behaving as an inductor. So we should change the function mode to inductance, and here we have our value of inductance. In this case, for a frequency of 50 kilohertz, the capacitor is already behaving as an inductor due to its parasitic inductance. So let's go back to capacitance and to 50 Hz. And then we can set up the voltage bias. In this case, we can go up to 5 volts, for example, or even 10 volts with the LCR meter. However, this voltage is limited and it's maximum 10 volts. For cases where, for example, we need to measure with a higher DC voltage bias, we could use also a power supply. To do so, we go to the LCX, we go to the options, to measurement, and we change the voltage bias to an external source. In this case, then we go to our power supply, and here I have 20 volts, for example, and I set the output on. In this case, I'm injecting the 20 volts as the DC bias, and here I'm measuring the capacitance with this DC bias. Here we can see the measurement that the LCR meter is doing of it. Now I will explain how to characterize the capacitor using a sweep tool. So here we have the LCX sweep tool, where we can set the function. In this case, we are going to select capacitance, a measurement speed which will be slow. We can also set fast or medium. The cable length is 0 meters. The test signal level will be voltage. And here we define the level, 0.1 volts, the range if necessary, and a voltage bias. For this case, I will just set 0 for the voltage bias. Then I will configure the sweep. Here I just define the frequency. Starting frequency will be 50 Hz. The stopping frequency will be 1 megahertz, and I define 200 steps in a logarithmic spacing. I will measure the absolute value of the impedance, the angle of the impedance, the inductance, the capacitance, the resistance, and the dissipation factor of this capacitor. Now that all is set, I hit the start button. And as you can see, the sweep start and it start. And in the LCX, we can see clearly that the frequency is changing constantly. It's because the sweep is done, and we can have here the results. Now the sweep has finished and we have our final results. We can see clearly the transition point between the capacitive behavior of our capacitor and the inductive behavior. So we can see here that the impedance angle increases. It goes from -90, which is a capacitive behavior, until 90, which is an inductive behavior, and the same with the magnitude. This resembles to the graph that was shown before in the webinar. Also, we can see here that this transition point it's more or less at 25 kilohertz. Okay, so we've reached the last part of our webinar, and as the main conclusions we could draw of this, it's that in general, the use of wide bandgap semiconductors in power electronics brings many benefits. However, it's equally important to characterize these parasitic components in order to fully realize the potential of these technologies. An accurate characterization of the passive components is essential for ensuring reliable and efficient operations of systems governed by power electronics. By using an LCR meter and other measurement tools, engineers can minimize the effect of parasitic components and optimize the overall performance of the system. And by incorporating these measurements into the design process, it can be ensured that the intended behavior of the circuit is achieved. Thank you for joining this webinar. I hope that now you have a better understanding on how to measure parasitic components, and see you another time.